This intricate maze of pathways represents a common hurdle in physics. You're looking at a circuit diagram, trying to remember if this is the moment to add fractions or if the voltage or the charge remains constant. Today, we are resolving that uncertainty by working through a specific standard problem, Class 12 Physics, NCERT Exercise Question 2.7. We have three objectives. First, we will map out a parallel circuit with three capacitors. Second, we will calculate the total capacitance of that combination. Finally, we will determine the exact electrical charge stored on every capacitor in the system. Successfully solving this specific problem provides the clarity needed to apply these rules to any parallel circuit you'll encounter on a final exam, removing the need to second-guess your calculations. To start, let's look at the data provided. We have three capacitors measuring 2 picofarads, 3 picofarads, and 4 picofarads. They are connected in parallel and powered by a 100-volt supply. This schematic shows the physical setup. The 100-volt power source branches out to three parallel rungs, with our capacitors, labeled C1, C2, and C3, each occupying its own path. Part A asks us to find the equivalent capacitance. This is the total capacity of the entire combination if it were functioning as a single component. A frequent error here is attempting to use the reciprocal fraction formula. That specific operation is only used for series circuits, not parallel ones. In a parallel circuit, the rule is additive. To find the equivalent capacitance, you simply add the values of all individual capacitors together. Our formula is C equivalent equals C1 plus C2 plus C3. When we substitute our values, 2, 3, and 4, the total equivalent capacitance is exactly 9 picofarads. This happens because parallel branches provide more pathways for charge to flow. By adding these rungs, you are increasing the total system's ability to store electricity, making the final result larger than any single capacitor in the group. In Part B, we need to calculate the specific amount of electrical charge stored on each of these three capacitors. As the blue highlights show, the defining characteristic of a parallel circuit is that the voltage across every branch is identical. Each capacitor is connected directly across the 100-volt supply. To find the charge, represented by Q, we use the standard relationship, charge equals capacitance times voltage. Our formula is Q equals CV. For capacitor 1, we multiply its 2 picofarad capacitance by the 100-volt supply, resulting in 200 picocoulombs. We apply the same logic to capacitor 2. Q2 holds 300 picocoulombs. Finally, for capacitor 3, 4 picofarads times 100 volts gives 400 picocoulombs. While these values are correct, many exams require answers to be expressed in standard units and scientific notation rather than picocoulombs. Since pico represents 10 to the power of -12, 200 picocoulombs is 200 times 10 to the -12. By moving the decimal point 2 places to the left, we reach the standard form, 2 times 10 to the -10 coulombs. Because the 100-volt pressure is identical on every branch, the capacitance of each individual component determines how much charge it can hold. We have now calculated every required variable. Review your own notes to ensure your final answers match the calculated data. On the summary board, we have our final results, an equivalent capacitance of 9 picofarads and individual charges of 200, 300, and 400 picocoulombs. To prevent future errors, it is important to keep the physical behavior of parallel and series combinations distinct. For parallel combinations, voltage is identical across components, charge varies, and total capacitance is their sum. Conversely, in a series combination, charge is identical, voltage divides, and total capacitance is less than the smallest capacitor. Understanding these two distinct frameworks allows you to categorize circuit problems by their physical behavior, ensuring your approach is based on the actual mechanics of the system every time you sit down for an exam.